Thank you, Peter. Thank you to the organizers for the opportunity to present. It's a pleasure. And what I hope to talk about today in the somewhat oxymoronic title of ZettaScale computing on Exascale platforms, in spite of that somewhat semi-facetious oxymoronic, I hope I can provoke some thoughts here about how we think about supercomputers as scalable systems, as engineered systems, and why I think it's time for a radical shift in the way we've thought about performance of these machines, but also obviously how we design them and what we design them for, i.e. a rethink of the very system design and design points. So the approach is going to be, I'm going to kind of get a bit deeper into this perspective of performance, introduce the term collective performance and interchangeably with effective performance. I'll define these terms shortly. In a nutshell, I'm going to try to motivate the community as a whole to move away from this unhealthy obsession about the performance of a single application. And I'll try to ground this in both technology trends, but also application requirements. And I'll try to say it's now time to think about the performance of many tasks, not a single task. And as many of you will know, Exascale is when you can take one particular application, one kernel, one task to the Exascale. And just to kind of disambiguate the title of ZettaScale on Exascale, what I'm going to argue is on the very same platform in which you can take one machine, one application to the Exascale, if you think of this collective performance of many tasks, you can get the effective performance of 1,000 Exascale systems or Exascale applications. But that's not going to come easy. It's going to require a lot of algorithmic, a lot of methodological developments. I'm going to argue that some of those methodological developments are... Thank you. There's going to be a lot of innovation at multiple levels. I'm going to focus on the system software aspects, hence the radical cyber tools component. And what I'm hoping to do is, rather than just throw some developments at you, motivate the software developments for future systems through a series of examples to show you that this ZettaScale on an Exascale, well, we don't have Exascale, so we won't have ZettaScale, but at 10 petaflops, we're starting to see capabilities emerge at the petaflop range, where you can start seeing multiple tens of petaflops. So that's the context. So let's step back for a second and just remind ourselves that historically, supercomputers, scalable computing, have been designed for two types of scaling, two types of performance. Namely, you take a particular problem and you solve it quicker, faster, and this gives rise to strong scaling. Or the other scenario is that of weak scaling, where you take a larger problem, but you solve it in the same time that it takes to solve a smaller problem. So, hey, why not solve the larger problem, right? But both of these have historically been around a single task, right? Can you take a single task and solve it in the strong and weak scaling? Again, work with Peter over the years kind of impressed upon me the importance of ensemble computing and high throughput computing. And these are very foundationally distinct from a single task. There's multiple tasks involved, and the design point, the performance is very different. But I'm going to generalize ensemble computing and high throughput computing into workflows and campaigns. And just some terminology, happy to point people to the distinction between ensemble computing and high throughput computing. In a nutshell, the idea is that high throughput computing is what I call I4, identical, idempotent, insensitive to order, and independent of each task. Ensemble computing introduces some level of coupling. campaigns and workflows are, if you will, not just coupling, but also dependency. So we just got the terminology, hopefully, all together. So we're going to focus on campaigns, which are a set of workflows, and a workflow is a set of many tasks with well-defined dependencies. Okay, so let's talk about the trend, why we have to think with a fresh perspective. I'm sure everybody knows about the end of Dennard scaling, end of Moore's law, different ways of talking about it. But the free ride that high performance computing has come to rely upon, well, is over, simply put. And whether you look at this in the form of, if you will, the projected performance of a single node, or you look at, on the right-hand side, the kind of plateauing of, the plateauing of what is called the single-threaded performance. Either way, business as usual is no longer possible if you want to extract performance. And we've heard even today, but also how people have moved towards GPUs, and that's going to give us a generation. But there are consequences of this architectural churn, right? Every time there's this architectural churn, there's an immense amount of human effort and cost in re-engineering your codes. And we saw some very nice examples of that. But when you put a dollar value or a euro value or a pound value onto that, it's highly non-trivial. And I argue, and would love to hear different points of view, simply put, I think it's unsustainable to have to re-engineer the suite of scientific code every time there's a major architectural change. And we've had some, we're suffering through some, and we're going to suffer through many more. And so that's why we step back and we start asking, if this is unsustainable, can we start thinking about beyond single application task executable performance? And interestingly, I think there's been a lot of development, which all of us, unless we've been living under a rock, have probably come to learn, appreciate, and even engage in, is namely the fact that there's been this immense set of advances in machine learning. And so I pose as a specific point of view here, can we use machine learning to enhance the performance of HPC simulations? And I hope this is very, very clear. I'm not saying the raw flops of a single task. To me, and I want to be deliberately, if you will, both irritating and controversial, to me that is boring, right? I want to think about the performance as a whole, a radical perspective to performance. And so can we use machine learning to enhance the effective performance of a single HPC? So there's a collective performance of everything put together, and then there's the effective performance of a simulation. And here it's important to ground effective performance as, can we get the same science for the amount of computing? And I'm going to show you through a series of examples that this is not a rhetorical question. My team and others are already getting 10 to the power 3 effective performance, and the state of the art is already 1 million to somewhere between 1 billion. But again, this raises a lot of questions. Okay, so now we change track and start moving much more quickly with the context hopefully established. I'm going to argue that there are at least 3 different ways in which machine learning is going to couple to HPC simulations. At the finest level, you're going to take a part of a HPC simulation, let's say computing the Hamiltonian or some part, you're going to substitute a part within a simulation with a learned model, a surrogate, typically a neural network. And that, in a way, is saying you're taking the most expensive part of a simulation, using a neural network to essentially compute the same physics, same phenomena, but at orders of magnitude lower cost. So you've learned some aspects of it. And I'm going to give you some very simple examples of how that happens. My real focus is on the second and the third, to try to say machine learning is going to be used to in this ensemble mode to not just improve maybe a single ensemble member, but more importantly, the swarm of ensembles and their trajectory in phase space improve the steering and guiding of these ensembles. So learn something which then tells us where the next simulation, next ensemble member should go. And remember, I introduced some terminology. A campaign is a set of workflows. So sure, I'd love to improve a specific workflow of an ensemble of simulations, but the real goal is going to be in the context of, can I improve a campaign, an end-to-end science application? And I'm going to talk about the COVID-19 therapeutics, again, worked on along with Peter, as an example of improving the campaign as a whole, and as a driver of some of the implications of the system software and middleware that supercomputers have got to support. Okay, so let's start with the first example. Very simple, very quick. Global climate models on the extreme left-hand side are, if you will, simulations, longitude, latitude, future temperatures. You can create a neural network adequately trained, and lo and behold, you can then pose questions once it's adequately trained. I'm glossing over all details. What is the, let's say, change in temperature at a given location, latitude, longitude at a given point in time? And long story short, to within bounds of accuracy, more complex the model in a way, the surrogate, the neural network, is able to give to within the bounds of accuracy the same answer in significantly lower computational costs. And that's what the y-axis is telling you. The x-axis is for different models, focusing on the extreme left-hand side, the global climate model. And you see that there's up to a 2 billion factor improvement of running a full global climate model, circulation model, sorry, with a surrogate, and for certain parts you get the answer. Now, I know this raises questions of, do you understand the mechanism, so on and so forth? Sure, we'll talk about all of those in a different context, but the point is, for a specific prediction, you are able to substitute a simulation with a surrogate and get your billion order speed ups. So that's just, again, a warm up. And this is obviously not my work, but work of a set of colleagues from essentially all over the world. As I said, I want to focus on the second part, where you've got a lot of simulations and you want to steer the simulation. So remember, what we're doing in ensemble mode is running many instances of a simulation. They're similar, but not essentially identical, maybe varying in the number of, in some parameters, some other conditions. And in addition to just a replicate, there's some level of interaction. There's some intermediate data that's generated, there's intermediate data sharing, and then there's some guiding based upon the results of these intermediate states, which determines the next stages or maybe the next parts of phase space sample. And that's shown in the bottom right-hand corner in the schematic, is that if you don't interact or couple at periodic intervals, then you grow through this kind of grayish part. But if you're able to kind of course correct intermittently, then notice you get this greenish, and you're able to explore more of phase space. So that's a schematic, and y-axis higher is better. Lots of details, not getting into the details. I hope you get the schematic idea that if you can run a large number of ensembles at very infrequent state intervals, have them share their state, and then based upon that shared knowledge, steer those simulations, then you're likely to do much better. Okay, so here's again a toy example where 4 different proteins, or small proteins, we say we want to fold them, right? So one way would be to fold them using single simulations. The second approach would be to just run an ensemble of them. And the third would be to run an ensemble of them, but the ensemble intermittently interacting and course correcting, right? And so that's what this schematic on the right-hand side shows, is that you simulate a bunch of them, you analyze, you kind of, based upon what you've learned, you decide whether to go back and steer in a different part, and you continue until you're done. So I hope the simple workflow makes sense, right? And again, the question then becomes, how should you determine whether you've done well enough, or how should you determine where to go in? And this is where going from simple linear algebra approaches such as PCA, principal component analysis, to kind of see how much of phase space you might have covered, to a more sophisticated deep learning approach where the network is learning aspects and facets of the trajectory and the phase space covered. You use a deep learned model, in this case StampNet, we won't get into the details, to help you answer the questions that you pose. And again, as I said, this is a toy model, but we do this for 4 different proteins, and long-winded way of saying that in each case for these 4 different proteins, the folding happens at least a factor of 10 times faster, right? So the different things you see on the right-hand side, each of the 4 proteins, but the red line and the blue line represents, the vertical, sorry, represents the first point at which folding occurs, right? And you can see that the red is always significantly less than the blue line. And that's trying to show you that the red line representing the adaptive ensembles, and in this case, using a deep learned model, tends to get you to your folded state and a known state much quicker in terms of the total computational cost, which is on the x-axis. So nothing profound, nothing unexpected here, but nice to ground our ability in a well understood problem before we go to something more sophisticated. And what is that something more sophisticated? Well, let's think about the spike protein when studying the coronavirus, COVID. And here you have trying to understand more complex phenomena. This is, as you can see, a much more complex, I would say, biophysical system than one of these very simple proteins. And it's not just about folding, but it's about complex macroscopic reorganization of what is called the knee motion. And exactly the same principles, though, as talked about in the context of protein folding, apply here. You run molecular simulations, you analyze the trajectory based upon these neural networks, sophisticated neural networks, and based upon the analysis, you guide an ensemble of simulations towards another part of phase space. And then the upshot is, no time for details, is do you actually see more confirmations in lesser amount of computational time? And we run this on a large supercomputer at approximately 3,000 to 3,000 nodes, which, if you do the numbers, is about 200,000 cores. So quite large scale, and we were able to show that you're able to get at least an order of magnitude improvement. So not just for simple proteins of the earlier type, but real meaningful systems are also amenable to this methodology. Okay, so now let me try to pack things together and come to the campaign where it's now not just a single workflow, but you're really talking about trying to bring insight into a very important societal and intellectual grand challenge, namely therapeutics for COVID-19. And again, a shameless plug-in for the National Virtual Biotechnology Lab, a Department of Energy activity of which we've been a part, and many different activities, but the part we've been co-leading is the supercomputing and AI for design of targeted therapeutics. And whereas Donald Trump yesterday on his way out had, well, let's just say the set of bad characters and actors were getting their pardons. Maybe one interesting thing on the way out was that the NVBL was given the Energy Secretary's honor for their contributions to the COVID-19 activities. Okay, so with that, so what is it we're doing? Again, this is work done in collaboration with Peter. The idea, very simply put, is there are many possible drug-like compounds candidates. How can we effectively screen something like 10 to the power 60 plus possible candidates and reduce them to a handful, a set, a few orders, a few hundreds, where we can then try to understand their possible efficacy, right? And there's not a chance in hell you can screen brute force 10 to the power 60. So we come up with a campaign that has multi-fidelity, multiple stages, that takes only promising candidates through the more expensive stages. So start cheap, you can do many, end expensive, you can do a few, but you must have a nice filtering mechanism to ensure only the most promising candidates go forward. So you get the whole idea. And what we're going to try to do here is just give you a high level overview of what these stages are. So stage one, cheap and cheerful, high throughput ensemble of docking calculations. And this is to just identify the small molecules, the hits. Then we do in stage two, the AI-driven molecular dynamics that I talked about to try to improve our confidence, reduce the uncertainty with which we may, and thereby improve our filtering. And then stage three being the most expensive, where we do full physics atomistic calculations, the binding free energies of the promising leads. Right, so that's the three stages.
You've got 5 minutes left. Is that okay with you?
That is okay, Peter. And so just kind of going through the fact that there's this campaign comprised of 3 stages, high throughput ensemble docking, AI-driven molecular dynamics, and then the binding free energy. And the reason why we have to think about these 3 very different types of computational activities, workflows, is kind of captured here. I hope you see on the right-hand side the different methods. And if nothing else, please notice that the cost per ligand is drastically different going from, let's say, docking to a binding free energy cost over several orders of magnitude. So that kind of meets the requirements of a pipeline where downstream is expensive but more accurate, so you put in more. But you're going to run these different methods at the same time. And how do you kind of then do the load balancing? How do you do the management of many different instances of these tasks, of these workflows, beg your pardon, but very different computational costs of each workflow. And just to set the scale before I give you some quick insight into how we do this, is this process that is as part of the NBBL has gone through about 100 billion docking calculations. And that's a non-trivial, I do not know of any published literature paper that has gone above 1 billion. So we're talking about 2 or 3 orders of magnitude more docking calculations. And this number is already significantly outdated. It is closer to 10 to the power 12 than it is to 10 to the power 11. Just to, again, set the scale, we're talking about running on about 8,000 nodes, and 8,000 nodes translates to about 4,000 cores, right? And so this is a whole machine. And so you're starting to see that about 2.5 million node hours. How do you run a campaign that consumes 2.5 million node hours, right? And this is all kind of has an experimental component. So why is this a computational challenge? Why does this force us to rethink our supercomputers? Well, I state the simple fact that you can't just go to a vendor, you can't just go to a company, or for that matter, any academic group and say, give me the software that can run things at this scale. This many different calculations, this many different types of calculations with the kinds of properties I've alluded to, a heterogeneous mix of AI simulations, ensembles, mix of very short running, but also very long running tasks, simply there aren't any turnkey solutions that you can get off the shelf. And that is where our research comes in. How do you build the tools and the software that allows supercomputers, which have historically been designed for one large task at a time, remember, top 500, unhealthy obsession, to doing something at the scale I've just shown you, right? And each of these components, as I've mentioned several times, has very different characteristics. Some could be GPU intensive, some could be CPU intensive, but they have to all run together, and there's a lot of coordination. Not to mention the fact that there's an inversion of sorts that's happened. You don't just have supercomputers generating insight from simulations, but you have supercomputers whose role is to run simulations not for insight, but supercomputers to run simulations merely as input data to train a model that will then substitute the simulation. So you're training your replacement, right? We won't get into the economic arguments there, but supercomputers will become merely powerful generators of data for ML models, not exclusively, but also, right? And this is where the radical cyber tools comes in with this perspective of what it means to use a supercomputer effectively on societally important problems such as therapeutics of COVID. We're designing and implementing the tools. And this is just quickly in the last 2 minutes to show you that even within the cyber tools family of tools, there is no one single solution. Here are 3 different launching mechanisms that we've had to employ for the 3 different types of workflows I've talked about. On the extreme left-hand side, there's the solution we do for docking. On the extreme right-hand side is the solution we use for the ensemble work with Peter. And in between, this is the solution we use for the AI-driven MD. They're very similar, but they're not identical. They have different design and performance points, right? And so just trying to start to wrap up, this is an example of trying to show you how even within docking, which is just a kind of a very simple exercise, when you run at scale at 8,000 nodes, you can see that over the course of a few hours, you end up over performance that varies over 2 orders of magnitude. And I'd like you to look at the docking rate on Frontera, where at the worst you have 0.2, and at the best you have something around 17.45 million dollars. Supercomputers do not assume such wide variation in single kernel application. This is just a way to tease and reinforce that the whole concept of performance has to be revisited if you're trying to do the campaigns of the type we're talking about. Okay, so in the interest of time, I just want to very quickly mention one other work we've done with Peter, namely the fact that you now have campaigns comprised of workflows. Some workflows might be GPU intensive, some workflows might be CPU intensive. And traditionally, people have said, okay, we'll run the GPU workloads at one time, and then we'll run the CPU workloads at one time. You simply do not have that luxury at the scales. Otherwise, you're going to be leaving 4,000, 6,000 nodes, either CPU empty when you're focusing on the GPUs, or GPUs empty if you're focusing on the CPU. So you've got to run them together. And this requires thinking at a campaign level, so you can run multiple distinct workflows with different computational requirements together. And so this is just to show you that Radical Cyber Tools is able to support the 2 variations of binding free energies that Peter's teams come up with at these large scales, and long way of saying that we can multiplex them and in the same amount of time run both workflows to completion as opposed to one after the other. Okay, so shameless plug-in for a very recent project that the DOE has commissioned, but it's an important conceptual change. It's a nod to the fact that workflows at exascales are first order requirements. And that is why halfway through the project, the DOE said, let's step back. Let's commission a exascale project focused only on workflows tools. I'm proud to point out that Radical Cyber Tools is one of those components. Look us up on exaworks.org. Let me start closing out. Introduced the concept of effective performance as a type of collective performance, and showed you how machine learning can be coupled with these simulations to improve the net performance. It's when you think about effective performance versus raw computational performance, you start seeing why ZettaScale is possible on an exascale. Reimagine the entire software stack that simulations, HPC, and supercomputers are going to be doing traditional simulations, as well as generating data for training powerful models. And all of this means that we have to step away from this unhealthy obsession of the performance of a single task and start thinking about how we optimize the collective performance of these workflows en masse. Thank you very much for your attention. I'd be glad to take questions.